All right. So yesterday we were talking about W59 and I had to do some of that for homework. We were talking about calculating here FG and figuring out what little g was, kind of a shorthand for big ugly. So let's just wrap that up because we're cut a bit short. Uh, Based on question 0 from W59, which you've done by now, we figured out that if you were on Earth, and basically we're always on Earth, so this is a useful recognition. If you're on Earth, then big G, mass of the Earth, and your distance from the Earth's center are always the same three numbers. So rather than multiplying and dividing and squaring those three every single time we calculate FG, we could instead realize what those three are together, which we approximated 9.83. You got that on the homework. Little extra credit over here if you want to take a stab at it. Why is that slightly different than 9.81, the number we accept and use? But anyway, basically 9.8, if we're going to go to two sig figs, then we don't need to use big ugly all the time. We got a quicker, easier way to do it. But anyway, let's get over to a second piece of conversation, and then we'll come back to that piece in the end. We'll follow the order of the notes. The order of the notes is that the meter per second squared and the Newton per kilogram, kind of the same thing. And let's see. Let's jump over here. We did talk about that yesterday. Let's jump over to this first, then we'll come back to that business again. We want to talk about drawing the gravitational field. So drawing the gravitational field is just the way we represent what happens when an object with mass goes near another object with mass. So basically, we have this little make-believe character we call Massey. Massey's got a smart-looking mustache. There you are, Massey. All right, so if we take Massey and put Massey anywhere near another mass, so Massey's make-believe, but if you just imagine putting like a mass out here, and maybe one over 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 here. Look like birds flying, right? So if you put masses, test masses, Massey, this make-believe thing, if you put test masses near the Earth and just let them go, what would happen? And what would happen basically tells you where the gravitational field points. So here's a let's look here, a little simulation of this. So we're going to add, here's a sphere like the Earth, and we're going to add the gravitational field arrows, vectors, all around this. Now, what you should notice, yeah, it's a lot to look at, but what you should notice actually is the closer you are to the object, the longer the arrows. That actually means, let me try to line this up all in one plane, kind of here. You see you get longer arrows, medium, and shorter. The farther away you go, the weaker the gravitational field is, and actually the weaker the gravitational field strength, which is what we're studying. The other piece you should notice is that no matter where you are in this picture, all of the arrows, all the vectors point toward the object. So the gravitational field always points toward the object. And if you were to put a particle in that gravitational field, a massive particle like Massey, or make-believe Massey, let's add them, what would happen is it would follow those gravitational field lines to the object, to the large mass Earth or sphere or whatever it is there. Okay? So actually you're seeing what Massey would do right there. Good. So the quick answer to this, what would Massey do? Well, I'll do it with arrows. No, and there we go. This sort of arrow, that's what we want. Massey would just go toward the larger mass Earth. So you would just have an arrow drawn directly toward the center of Earth that ends on the surface of Earth. This is just a convention on how we draw gravitational field lines. So where would Massey go here? It would go toward Earth. It would actually go toward Earth's center. So we draw an arrow toward Earth's center and end right on the surface. Draw an arrow toward Earth's center, end right on the surface. Draw an arrow toward Earth's center, end right on the surface. Draw an arrow toward Earth's center, end on the surface. So we don't need to end there. You know, you can draw one here. You can draw one. You draw as many as you want, really, for our schematic, for our purposes. Now, unlike what we saw over here, where the field strength was represented by the length of the arrow, we're not drawing separate arrows. We're actually drawing field lines. The strength is represented by the spacing between the lines, essentially the density of field lines. Now, you don't really have to worry about that in our course, not when it comes to gravity at least. But here, basically, you can tell near the Earth, the lines are closer to each other. And when you move farther away, the spacing between the lines is bigger. And that's the way we actually represent the field strength. But anyway, gravitational field strength is not limited to the Earth. Muffin Cat has mass. Therefore, Muffin Cat also has gravitational field lines around him. In fact, what we need to do is identify Muffin Cat's center, which is maybe somewhere in this soft pillowy region. And then we start drawing field lines to it, ending at his surface. So there's a gravitational field line for Muffin Cat. There's a field line for Muffin Cat. There's a field line. There's a field line. There's a field line. There we go. So Muffin Cat's got a gravitational field around him. Boom, there are the gravitational field lines representing the gravitational field around Muffin Cat. Now, the whole idea of a field is a little complicated. We won't really flesh that out till we get over to electricity and the electric field. But for now, this is pretty easy. It allows you to answer one of those simple questions on the homework, which you skipped before. Now I want you to do it. There were a couple questions on the homework I told you not to do. Finish them all. There were like, I don't know, 2 questions, I think. One of them actually was just a multiple choice about which way the field arrows point. Boom, here it goes. Okay. Now, we're not going to get too fancy with talking about field lines right now, and we're also going to skip this little section because you're going to do a version of this when you do the normal force. Let's go to the last page here. We were very quick talking about this, and the truth is you were probably fine because, again, repeat, if we have an object that is on or near Earth, most of our problems are near Earth's surface. We don't need to go through the rigmarole. We don't need to call on Big Ugly. Big Ugly is a wrecking ball. It takes care of any gravity problem. But we don't need Big Ugly when it's a simple problem that's near Earth. Because we've already figured out that near Earth, these 3, g times m over r squared, actually simplify to give you little g. Give you 9.81. So what you can do instead is call on our buddy right here, our simplified version of this. This is our shorter version of the equation. We call this equation, well, if we need a little help here, we don't need Big Ugly. We know we're near Earth's surface. We know little g. We don't need to do all this gm over r squares. We don't call that, hey, shouty! That's right, we call him shouty. Shouty. And it says right here, whether you're on Earth or elsewhere, if you know little g. So when I say or elsewhere, if you're on Earth, you know it. 9.81, we've been using it. If you're elsewhere, that means like if you are here, boom, you're on Jupiter, and they tell you the gravitational field strength is 26 newtons per kilogram. Well, now you know it. If you know it, you call on that shouty. Shouty. And that makes your life much easier. So these questions, quite simple down here. I know you were good to go on these. I'll just hit the givens real quick. Determine the force due to gravity. Boom. First given you should have written down is Fg equals question mark. Newtons. Next, acting on a 50 kilogram mass. Trust the unit. If it's kilogram, it's the mass. Boom. Mass is 50 kilograms. And now this is on Jupiter. You don't know about Jupiter, but the problem told you about Jupiter, so now you know about Jupiter. Where the gravitational field strength is, gravitational field strength, little g, 26 newtons per kilogram. And of course, this is a very simple equation. The only thing you got to watch out for is when you cross multiply, don't mess it up. When you cross multiply, don't mess it up. All right, let's go from here. Now, the next question, what is the magnitude of the gravitational force? Oh, there it is again. Gravitational force, Fg, question mark, acting on a 2 times 10 to the third kilogram. Oh, it says kilograms. That's a mass. 2 times 10 to the third kilogram mass. 2 times 10 to the third is just 2,000. You could write as 2 times 10 to the third, or you can write 2,000. But don't confuse. The 2,000 is separate from the kilograms. You're slick right now. Go. All right. And that is freely falling toward the surface with an acceleration of 11.2 meters per second squared. So you may come over here and say, oh, acceleration. Well, it doesn't quite look like shower. And we kind of want it to. So what's going on here? 11.2 meters per second squared. Well, the recognition is this. If your planet is here and here's a meteorite, and if it's falling downward and its acceleration is 11.2, well, it would only accelerate at 11.2 meters per second squared if the gravitational field strength at this location right here were 11.2. And when we talk gravitational field strength, we tend not to say meter per second squared. We tend to say Newton per kilogram. So if the gravitational field strength were 11.2 Newton per kilogram, so that must be the case here. You only free fall at that acceleration if that is the gravitational field strength that at that location. FGMG, boom, done, do it. Last question. The gravitational field strength on the surface of the moon. That's gravitational field strength. It's now on the moon, 1.62 Newton per kilogram. Trust the units. That's little g. Newton per kilogram. Now, I want you to recognize something. Let's get that. Here we go. I already have it written under there. Look at it. Isn't that nice? Well, we're going to write it anyway. 1.62 Newton per kilogram. Now, one thing I did not mention in the previous problem, which I should have. This problem was about planet X or wherever it is. This one here, it's about the moon. The gravitational field, I would subscript a little m over here for the moon. Really would. Because this is not the same as the Earth. And you're used to doing G is 9.81, but that's true on the Earth. And this is why it's important. The ship has a weight of 10 to the 6 newtons on the moon. So when you're writing your FG, this is particularly on the moon. As you've seen in your FG versus R graphs, weight can change depending on the location. So you can come over here, pop your 10 to the 6. That's a million, by the way. 10 to the 6 newtons on the moon. And the question asks, what would be the mass on Earth? Mass on Earth is our question mark given. Of course, in kilograms. Now, some of you may recognize immediately, oh, okay, I got this. Good. However, if you don't, or even if you do, let me point one thing out here. When you use your equation, G is Fg over m. A general rule of thumb is your equation should have coordinated givens. If you're going to plug in G for the moon and Fg for the moon, then you're going to get out mass on the moon. And of course, these are easy numbers. Put your 1.62 here, put your million here, cross multiply, get your mass on the moon. Now, how does that connect with mass on Earth? And so we take advantage of this connection, this fundamentality of it, if you will. Mass, of course, stays the same. So mass on the moon and mass on the Earth are the same thing. So in fact, your equation will solve for mass on the moon, but mass on the moon is mass on the Earth. And so you will get that 6.2 times 10 to the 5th, 620,000 kilograms. And that's that.